Hello, good morning, good evening, good afternoon, everybody, wherever you might be. Well, now it's time for a grand finale of this academic year. And the grand finale will be performed by Robert YUNCKEN from France. And his talk will be crystal clear about compact semi-simple Lie groups. The floor is yours. Take it away.
Thanks very much. I didn't realize I was the season closer, Piotr.
Yeah.
You're doing this in alphabetical order or something?
Yeah, the terminator of the academic year.
Okay, very good. Well, okay, yeah, so here we go. So thanks very much, Piotr, and to the other organizers, of course, for inviting me to speak. As Piotr says, we're going to take a crystal clear view on compact semi-simple Lie groups. And when I say crystallizing compact semi-simple Lie groups, I really mean crystallizing the function algebra and not the representation theory of compact semi-simple Lie groups. And this is the second talk this season on crystallizing function algebras of compact semi-simple Lie groups. There was one earlier this season by Paul. At the point of view that I'm going to take here is a little different. It's using really the crystal basis theory of Kashiwara and Lustig, and it's come out of work that that was done with Marco Matassa, who is here as well at the moment, and will probably have many insightful comments to add as we go through. Well, we'll see. In any case, let's go for it. So I'll start with an executive summary, just to tell you what the goal of this project is. So the overarching goal is to make what I call a set theoretic version of representation theory for semi-simple Lie groups. So set theoretic is a phrase I'll have to clarify a little as we go on. The idea is to reduce the operators that you get in representation theory from linear maps between, on Hilbert spaces, down to just finite maps on, ordinary set maps on some countable set. So I'll explain that as we go on. That's the general philosophy of crystal bases in a theory, in a nutshell. So there's a bit of a...
Yeah, I'm trying to mute somebody. Should be muted. Wait.
Okay.
But go ahead, let's speak out loud.
Okay, yeah, I'll plow on. So as it says here in point 2, this idea of making a set theoretic version of representation theory is well known for compact semi-simple Lie groups, or if you like, for complex semi-simple Lie algebras. And this is the theory of Kashiwara and Lustig on crystal bases, which I'll get to in a second. But this talk is rather about the dual thing. So as I said at the start, it's about function algebras on the group K. But by the well-known quantum duality principle, the algebra of functions on a group K, a compact group K, corresponds to the Pontryagin dual algebra, so the C-star algebra on the Pontryagin dual group. So first of all, in the classical case, the Poisson dual group of a compact group K is the AN group that you find in the Iwasawa decomposition KAN of the complexification. And what happens by some magic is that when you quantize this compact group, this Poisson dual gets turned into the Pontryagin dual in the sense of quantum groups. And so you could interpret this whole talk, instead of being about the function algebra of KQ, the quantization of K, you could consider it as being the C-star algebra of ANQ, so the representation theory of the AN group. And that would be a different way of seeing this talk, even though the objects end up being the same thing. Okay, so that's what we're going to get to. But to start with, we should begin with a quick tour of crystal basis theory. So let's do that. So this is a beautiful discovery independently by Kashiwara and Lustig. I think it was in the 90s, if I'm not mistaken. So I'm going to approach it not in the way that they approach it, which is a very algebraic way, but in a more operator algebraic way, since this is supposed to be a group of operator algebraists here. So I'll explain in a slightly different way how you can make their crystal basis constructions. So what I want to do is start with a compact semi-simple Lie group. Let's make it connected and simply connected to avoid pathologies. And you should just keep in mind the example of SUN, or even SU2 to begin with would be a great example. And then little g is going to be the complexification of its Lie algebra. So in the case of SUN, this will be the Lie algebra SLNC. What this means is, just by the usual linearization process, the representations, irreducible unitary representations, say, of the compact semi-simple Lie group K will be in bijection with the irreducible representations, finite dimensional, say, irreducible representations of the Lie algebra G. So studying the representation theory of one or the other amounts to the same thing. And we have this famous theorem that these representations, irreducible finite dimensional representations of G, are classified by their highest weight. Okay, and I'm not going to go through the whole highest weight theory. If you're not familiar with the highest weight theory, let's just take for the moment that there is some data, some linear functional called lambda, which determines these representations. So that's all very well. That gives just a list of the representations that you can have, but we might want more information. We might want some explicit structure, some explicit formulas for what these finite dimensional irreducible representations look like. And so for that, we have a whole bunch of results going back now almost a century. So it's almost the 100-year anniversary of the Weil character formula, which gives the basic information about the structure of this representation, at least in terms of the way the Cartan subalgebra H works. So the Cartan subalgebra, in the example we're thinking of, will be the diagonal matrices in SLNC. Weil gave an explicit formula for why this acts. And it basically decomposes into simultaneous eigenspaces for the action of this diagonal subalgebra, which is an abelian algebra, Lie algebra. This gives you what are called the weight spaces. So the simultaneous eigenspaces are called the weight spaces. And as we see above, the highest weight among those, so the highest eigenvalue, simultaneous eigenvalue in some reasonable sense, classifies the representations. And he gave explicit formulas for the dimensions of these weight spaces given a particular highest weight. Okay, but maybe you want more information. Maybe you want to know not just how the diagonal matrices act, but how the off-diagonal matrices act as well. And for this, the first explicit formula that we have is Gelfand and Zetland in 1950, who wrote an incredible 4-page paper with no proofs, but some beautiful combinatorial formulas that gives a very explicit combinatorial formula in terms of, if you like, hypergeometric functions, or more simply just quotients of ratios of factorials, for the way the simple root vectors EI and FI act. So EI and FI, in the case of, let's take GLNC or SLNC, it would be more or less the same thing. EI is supposed to be the elementary matrix with a single 1 in the I, I plus 1 slot. Have I got that the right way around? Yes, the I, I plus 1 slot, which is just above the diagonal. And Fi is the elementary matrix with a single 1 in the I, I minus 1 slot. Sorry, the I plus 1, I slot. So that it's the adjoint of the EI. So these are the elementary matrices, just super diagonal or just subdiagonal, and they gave explicit formulas for these without explaining how they came up with these formulas, how you might prove these formulas or anything. But of course, their formulas are absolutely correct. Okay, but the disadvantage is that this only works for GLNC, and then you might ask, well, okay, I want similar formulas for the other semi-simple Lie algebras. And okay, so this was done over a process of a period of many years, a couple of decades, as people tried to generalize this, first for ON and then SPN, and then all the classical Gs, so all the semi-simple Lie algebras of type A, B, C, and D. The exceptional groups were not done just because it becomes really painful to write down these formulas, even in the classical cases that I've just cited. Just finding the appropriate index parameter space for indexing the bases, the weight bases, is a real pain in the bum. And writing down these explicit formulas just becomes more and more heavy. And I think eventually people just sort of ran out of steam and went on to think about other things. So this was the situation until Kashiwara and Lustig came on the scene in the 1990s. And they revolutionized things completely by taking a completely different philosophy using quantum groups. And that's, of course, what we're going to talk about today. So the observation, which begins with physicists, Russian physicists, trying to solve the quantum Baxter equation, and then particularly with Drinfeld and Jimbo, was that these semi-simple Lie algebras admit quantization, so a deformation according to some parameter Q, such that when Q equals 1, you get an algebra which is just the universal enveloping algebra of G, and when Q differs from 1, you get some quantized version of this universal enveloping algebra.
Robert, sorry to interrupt you with the trial method, but are you sure your spelling of Lustig is correct?
Oh, no, I'm absolutely wrong. It's SZT.
Yeah, I mean, T, but they're non-commutative, right? Yes.
They're non-commutative, exactly. So yeah, I'm speaking to the wrong seminar here. Yeah, when Q equals 1, it doesn't matter, but
yes.
away from Q equals 1, you're absolutely right. It should be ZT. So yeah, they considered what happened as this parameter Q goes to 0 or infinity, where the official relations introduced by Drinfeld and Jimbo break down, but nonetheless, they were able to extract, in a way we'll see shortly, a way of taking a limit as Q goes to 0 or Q goes to infinity. And they noticed that the representation theory just suddenly simplifies massively, so that it becomes entirely set theoretic. You don't need the complicated formulas of the type of Gelfand and Cetlin and so on to understand how EI and FI are acting at Q equals 0 or at Q equals infinity. And then using those two extreme cases, they were able to do some impressive interpolation, algebraic interpolation, to obtain very explicit combinatorial results for the structure of representations, even at Q equals 1 in the classical case, which avoids all the pain that Pand and Hecht and Wong and so on were trying to do in the 50s and 60s. Okay, so let's do that, but rather than leaping into the algebraic theory, like I said, I wanted to do something, an approach which is more operator algebraic. And because I'm lazy, I'm going to just take a scan of some calculations that I did years ago. You can see here what a careful record keeper I used to be in my youth. This is a very explicit calculation of the representation of the Lie algebra SL3C of highest weight twice pi1 plus twice pi2, where pi1 and pi2 are the fundamental weights. So this is twice rho, if you like, where rho is the half sum of the simple roots. In any case, this is some 27-dimensional finite dimensional representation of SL3, irreducible. And I'm using here the standard notation where, so these little dots here refer to the different weight spaces. And the standard convention is that if there's a single dot like this, it's a one-dimensional weight space. And if it's a dot with a circle, it's two-dimensional weight space. And if it's got a second circle, then it's a three-dimensional weight space. So I have weight spaces of varying dimensions. And for reasons that I'll explain shortly, I needed to know exactly how the two matrices, lower diagonal matrices F1 and F2, act on these weight bases. So the Weil character formula tells you how the diagonal matrices act. I wanted to know how the off-diagonal matrices act, in particular F1 and F2. And so the action of F1 and F2 are given by the matrices in this scan. The horizontal ones are the action of F1, and you can see that those guys are just diagonal matrices, or at least as diagonal as a rectangular matrix can be. And the F2s are the arrows going down to the right. So these are not diagonal matrices anymore, but they're still bidiagonal matrices, as you can see in this middle line, or in fact any of the lines. The non-zero elements only occur on two diagonals, two adjacent diagonals in these rectangular matrices. And this is a consequence of the Gelfand-Cetlin formulas. In fact, if you look at the SL4 representations and you see how F3 acts, you'll see that they act by tridiagonal matrices. And if you go into higher rank, then F4 will act by tetradiagonal matrices, and so on and so forth. So there's some nice structure going on here. And if you write down, if you look at Gelfand-Ceplin's formulas, this is exactly what you get. The square matrices at the points here you can ignore for this talk. I didn't bother erasing them from my old scan, so they're just hanging around as a distraction. But I'm really interested in the way the arrows F1 and F2 act. Okay, a short digression, which is a little irrelevant to this talk, but I'll mention it anyway. Why was I interested in doing this tedious calculation? In fact, I was interested, this was work I was doing at the time with Christian Voigt, based on previous work I'd done on index theory on flag varieties. So we were interested in looking at the full flag variety of SL3, which is the space of lines within planes within C3. This is a compact manifold with a lot of nice structure. It's got two fibrations, natural G-equivariant fibrations, one where you forget the line and one where you forget the plane. Either way, you end up with a copy of CP2. You either end up with a space of lines in C3 or planes in C3, which are just dual to lines in C3. So you get two fibrations like this, each with fibers CP1, the Riemann sphere. I was interested in using the longitudinal Dolbeau operators, Dirac operators along these fibers to produce the famous gamma element in KK theory. Okay, that's not what we're going to do today, but I just mentioned this because what I really needed was not the Dirac operators on here, but rather the operator phases of the Dirac operators, so order 0 pseudo-differential operators rather than order 1 differential operators along these two fibrations. And if you do the calculations, everything here is completely G-equivariant. So you could expect that these two longitudinal Dirac operators are actually given by some representation theoretic construction. And indeed, this is the case. If you restrict to the various different K-types, which appear in the algebra of functions on this flag variety G mod B, what you find is that these two Dirac operators act precisely by the operators F1 and F2 on each K-type that I had drawn in the previous diagram. Okay, all this to say, firstly, studying these F1 and F2 operators is interesting for reasons of equivariant index theory. That's the first thing to remark. And the second thing to remark is it's not really the F1 and F2 that I'm interested in, but rather the operator phases. So if I go back to the diagram that I had here of a particular K-type, a particular finite dimensional irreducible representation of SL3, it's not this diagram that I'm really interested in. I'm really interested in taking these F1 and F2 operators, matrices now, once I've restricted to this finite dimensional K-type, and taking their operator phases. So that's what I'm going to do in the next scan here, and this is what you get. So these are the operator phases of the previous, the matrices in the previous diagram. And no surprise for the diagonal matrices, which are the F1s, you just get diagonal isometries, that is 0, 1 valued matrices with ones along the diagonal and 0 elsewhere. So that is the operator phase of the F1. That's extremely nice. The sad news is when you do the operator phase of the F2, which before was a bidiagonal matrix, well, when you take the operator phase of a bidiagonal matrix, everything just breaks. You don't have bidiagonal matrices anymore. You just have a mess. You just have some matrix where all terms are non-zero. And that's exactly what you see and exactly what I was calculating, excuse me, at that time with Christian. Okay, so we get these operator phases. Of course, I could express them as 0, 1 valued matrices if I changed my basis, but the basis would no longer be compatible with the 0, 1 matrices in the other direction. So either way, I have to make a choice, and one of the operator phases is going to be bad. So that's, okay, that looks like bad news, but it's going to get better shortly. I want to remark that, so you'll see here, for instance, that I've got one of the coefficients being 5 plus 2. That's not because I was incapable of calculating what 5 plus 2 was, but rather because, as I hinted before, what I was interested in is not really index theory on the classical flag variety, but index theory on the quantum flag variety, which means that the correct coefficients here, 5 plus 2, are not classical 5 and 2, the integers, but actually Q integers. So that's, in fact, all the integers that you see in these calculations are not actually integers, they're actually quantum integers. So I need to tell you now what a quantum integer is. I'll just remind you quickly. If A is an integer, then quantum A, or Q, the Q integer A, is just this Laurent polynomial with A terms right here, which can be expressed in a cute way above as this fraction, of course, this rational function in Q. That's nice because it lets me do it even if A is not an integer. but for many reasons, it's better to look at this Laurent polynomial, because in particular, when I take q equals 1, this is going to specialize to just the usual integer. So what we get is some generalization of the integer a in terms of Laurent polynomials or rational functions, if you like, such that its restriction at q equals 1 is the classical notion of a, and away from q equals 1, I get some fancy quantum thing, okay, which has been studied for decades, centuries, by number theorists and all sorts of other fascinating people, and shows up yet again here in the world of quantum groups in a way that we'll see shortly. And of course, you can do all sorts of other things with it. Quantum factorials will show up in this talk. There are also quantum binomial coefficients and quantum derivatives and quantum integrals and all sorts of other things. Okay. Now, yeah, we can jump to the quantized enveloping algebras. So I start with a classical Lie algebra, like SL n+1c of rank n. And I want to quantize it. So I indicated before that the right way of quantizing this is not with the Lie algebra itself, but with the universal enveloping algebra. So what we do is we write down the universal enveloping algebra of SL n+1c in terms of generators and relations. So here I've got my generators, the EI matrices, the FI matrices, and the diagonal matrices, so values 1 and -1 adjacent, which are the HI matrices in the Cartan subalgebra. And Chevalier and Serre showed that, firstly, they satisfy these matrices, satisfy these relations in the enveloping algebra. So yeah, I should probably not see them as matrices anymore. This is not matrix multiplication, but rather the algebraic multiplication in the enveloping algebra. Okay, that's easy to check, but moreover, that these relations are sufficient. They're a complete set of relations to describe this universal enveloping algebra in terms of these generators. And what this allows us to do is quantize things just by throwing in q integers into the Chevalier-Serre relations. So I'm going to take exactly the same set of generators. I'm no longer allowed to think of them as matrices because they don't satisfy exactly the same relations. I think of them just as some abstract generators for some abstract algebra, UQ of G. And they're going to satisfy exactly the same relations, except certain things will be quantized. So in the last two Chevalier-Serre relations, I'll replace the coefficient 2 by a quantum 2, which is just Q plus Q inverse. And I'm also going to replace this relation here, which used to be the commutator of these two matrices, EI and FI, gives you the matrix HI. I'm going to replace that with HI quantized. And that's something I'm only allowed to do as an operator algebraist. The pure algebraists don't have this liberty. They're not allowed to do this because the way I'm defining HIQ here is by functional calculus down the bottom here, using the same formula as on the previous slide for quantum integers, but now I'm doing a quantum element of an algebra. And if I'm a pure algebraist, I'm not allowed to take an algebraic function, a transcendental function of an algebra element. I can only take algebraic functions or polynomial functions even. So if I were an algebraist, I'll tell you what I would do. I would just replace my generators HI by a formal generator Q to the power of HI, which they tend to call KI. And now you can rewrite these generators and relations in a way that doesn't use any transcendental functions of KIs. It uses only polynomial functions of the generators, and so it's well defined. But I kind of like the operator algebraic point of view here because it gives you a sort of spectral insight into the way these things are being quantized. Mm-hmm. Okay, so we just take a quick pause there and catch my breath and see if there are any questions.
So these matrices, before they vanished, they were n+1 by n+1 size, right?
That's correct.
And I was running from what? From 1 to n?
That's right. I didn't specify that. I was running from 1 to n. So you get all the elementary above diagonal matrices, all the elementary lower diagonal matrices. And this here will be a basis for all the diagonal matrices for trace 0.
And who was first to come up with these quantum numbers? Because I have some vague impression that it's a very old story.
It's a very old story. So the number theorist, Ramanujan was proving facts about these, but it's older than Ramanujan as well. It goes way back. It's I couldn't tell you accurately, but I think this is
but it's ancient, yes.
It's 19th century mathematics, I think, at least. Yeah, that's the Q numbers, of course, and then the Drinfeld-Jimbo stuff is from the 80s or 70s and 80s. Okay, let's surge onwards. So now that we've got our quantum enveloping algebras, I can take EI, FI, and HI in this new quantum algebra. It turns out that the representation theory of this UQG algebra is basically the same as the representation theory of the classical UG algebra, in that, again, representations are classified by their highest weights, and they have exactly the same dimensions and exactly the same dimension weight spaces. So that this diagram that I had on the very first scan can be just reinterpreted as a representation, a formula for the representation of the 27-dimensional representation, irreducible representation of UQ SL3 with a particular highest weight, where all the, as I said before, all the integers here should not be classical integers, but they should be Q integers. So this is why I've written, for instance, 2 times 2 divided by 4. This is not 1. This is quantum 2 times quantum 2 divided by quantum 4, and so on and so forth. But other than that, all the formula remain exactly the same. You get a quantum analog of the Gelfand-Zetlin theory, so all the formulas just carry over by putting square brackets around all the numbers and Qs at the bottom, which is already sort of good news. We then get this slightly unfortunate formula again for the operator phases, which looks bad. But now what we're going to do is we're going to look at what happens when Q goes to 0. So I'm just going to take this scan, which is, like I said, calculations from more than 15 years ago, and I'm going to buy myself an iPad and redo this calculation on an iPad. But now I'm older and lazier, so I'm not going to calculate this precisely. I'm just going to look at the leading order term as Q goes to 0. So it's exactly the same diagram as this pre-iPad version here, except that I'm throwing away all the negligible terms as Q goes to 0 and just keeping the leading order term. Remember, all these things are Laurent polynomials in Q, maybe with some square roots, but okay. In any case, this is what you get when you throw away the negligible terms. The first thing you notice here is you don't get any terms with Q being to a negative power. This, with a moment's thought, is not a surprise, because these are supposed to be operator phases, and so they have to have norm at most 1. So all the coefficients as Q goes to 0 must be less than 1. I can't possibly have any negative powers of Q there. Okay, let's make that remark nonetheless. And what that means is, if I now, instead of taking a small q, I take a q equal to 0, I take the limit, all the terms apart from those that are constant equal to 1 are going to vanish, and I'll get 0, 1 valued matrices like this. So if I take the limit as q goes to 0, which according to Drinfeld and Jimbo is not allowed, the Drinfeld-Jimbo relations degenerate when Q goes to 0. You get divisions by 0 all over the place. It makes absolutely no sense. But nonetheless, so if I were to do this formula just with F1 and F2 themselves, this would make no sense. It would blow up. But because I've just used the operator phases of F1 and F2, everything works just fine. And I end up with limits which are just 0, 1 valued matrices, partial isometries, if you like. And the great news is they're all diagonal with respect to some basis, and again in some they're not all diagonal on the same diagonal, but they're all diagonal on some diagonal, and so that means that they're really just maps between basis vectors. I have a single basis for these weight spaces, unlike before where I had to choose a basis adapted to either F1 or F2. Here I can use the same basis for operator phase of F1 and operator phase of F2 at Q equals 0, which diagonalizes every single one of the operators in sight, so that instead of describing this in terms of linear maps, I can just describe it in terms of a set theoretic map on the basis. And that's this. So, what's happened here? Here I've got, for instance, in the center here, I've got this 3-dimensional weight space. I'm just going to write its 3 basis vectors here as 3 separate dots. And this diagram now, the arrow, which used to be a 0, 1 valued matrix here, I've just written down where every basis vector here goes, which basis vector is its image under the operator phase of F2 down here. So that now I can describe this representation for the Q equals 0 quantum group just as a set theoretic map on a set with 27 elements, which is much easier to deal with than operator phases of, rectangular matrices with Q Laurent polynomial coefficients. This is just set theory, it's a marvelous thing. So this is the observation of Kashiwara and Lustig, that this incredible simplification happens if you renormalize in the right way. So the renormalization I've talked about is taken operator phase. They had a different renormalization, which I'll talk about in just a second. But it all degenerates at Q equals 0 to give just a set theoretic map. It's not a totally trivial set theoretic map. If I start at this highest weight vector and go operator phase F1, operator phase F2, or operator phase F2, operator phase F1, I don't get the same basis. So there's still some non-commutativity going on in this set theoretic map. But clearly it's a much simpler object to deal with than the original guy. Okay, so that's the operator algebraist's understanding of what a crystal basis is. This basis here at Q equals 0 is called the crystal basis. Well, it's more elaborate than that. I'll give a proper definition in just a sec. But that's the basic idea. Okay, if this were not an hour and a half long talk, I think I would skip the next 2 slides, but it is an hour and a half long talk. Piotr made the terrible mistake of giving me an extra half an hour. So I'm going to give the official definition as quickly as I can. If you're an operator algebraist and you hate algebra, now's the time to go and take a toilet break or make a coffee or something and come back in 5 minutes. This is not at all essential to the rest of the talk, but I'm going to mention it because it's good culture, and this is the way Lustig and Kashiwara came up with this stuff.
Yep.
So let's go for that. So what did they do? They didn't think of Q as being a parameter between 1 and 0 and infinity. They thought of Q as being a transcendental, what am I trying to say? A variable, a formal variable. And so that they define their quantized enveloping algebra UQG instead of over the field Q with over the field of, say, of complex numbers, as I did before, with Q being a fixed parameter. They define it over the field of rational functions in Q, so that they consider all of them at once. It's, the algebraist's version of a continuous field of C-star algebras, if you like, or continuous field of star algebras. I don't know how to describe it. Continuous field of algebras, just perhaps is the best way. You could happily take this over the field of rational functions with complex coefficients, but in fact you only need rational coefficients because everything in all the formulas will be rational. So they define first their quantized enveloping algebras in that way. They remark that the irreducible integral, I won't say what integrable means here, it basically means finite dimensional with a little bit of extra condition. Integrable UQG modules are still classified by highest weights. As we said before, the highest weight theory is independent of the parameter Q. It's the same for all Q. It'll just change the formula slightly with, with some Q integers showing up. And then instead of taking an operator phase like I did, which they're not allowed to do because, again, that's a transcendental operation, they take an algebraic version of the renormalization, which goes as follows. So you start with SL2, as always. The representations, irreducible representations of SL2, we know very well. They're just indexed by their dimension. So this is VM here is the representation of dimension m plus 1. I'm going to fix a basis, a weight basis for this representation, which are given just by, well, V0 being the highest weight vector, and then the successive V1, V2, and so on being the image of that under the F operator, so the lower diagonal matrix. But I want to renormalize that. So again, if I were an operator algebraist, I renormalize that by taking the operator phase of F. But if I'm an algebraist, I can't do that. So I divide by some appropriate power of Q. Actually, a power of Q would work totally fine here, but you know, it's more natural in some sense to use this Q factorial instead, which of course to leading order is some particular power of Q. But okay, this is a good choice for how to renormalize your operators FQ. You should see this as an algebraic phase in some sense. Okay, so now we have this basis, weight basis, and we'll just define the two operators on this weight basis, E tilde and F tilde, just by partial isometries, again, if you like. We're just going to have 0, 1 valued matrices, which where E tilde raises the weight vector and F tilde lowers the weight vector in this ordering. Okay, so the F tilde is exactly the operator given by a renormalization of F, and E tilde is a renormalization of E in some other sense.
Sorry, that's a silly question. Would you be able to use E instead of F in this formula for your crystal basis?
Yeah, you could use E, but you'd have to start with the lowest weight vector instead of the highest weight vector and run up, and then you'd have to choose. Yeah. I think, yeah, I'd have to think a bit about what the appropriate renormalization would be. It might again be just 1 over k factorial, well, 1 over k plus 1 factorial in that case as well. Yeah, I think by some symmetry.
Okay. Yeah, just.
Yeah, it's totally equivalent. So what's really important is just, you know, what this appropriate coefficient is here to renormalize your different weight vectors. Exactly. Okay, so where do these guys live? You know, so for any particular irreducible representation VM, this gives you just an endomorphism of VM. But I could see these E tilde and F tilde as acting on all of these representations at the same time just by taking their direct sum. And if you're a quantum groups person, you might recognize that as being the algebra of functions on the Pontryagin dual of SUQ2. But again, an algebraist wouldn't say that. I mentioned that for the quantum groups people in this audience. Once you have this SL2 situation, you can take advantage of the fact that for a higher rank semi-simple Lie algebra, you have a whole bunch of inclusions of SL2 into your higher rank semi-simple Lie algebra, where you send E and F from SL2 into EI and FI in your higher rank group. And that's how you define the Kashiwara operators. So for a G semi-simple Lie algebra arbitrary, we can define the Kashiwara operators E tilde I and F tilde I to just be the images of these renormalized E and F operators induced by the inclusions of SL2 into G given by sending E and F, the usual guys, into EI and FI. Okay, and so that just straight away defines your renormalized EI and FI operators basically according to the same formula, but taking account now of just which with the restriction to a particular SL2 subalgebra in your semi-simple Lie algebra. So that's what Kashiwara does. And then, okay, a little bit of algebra. So amongst the rational functions f over g, I'm going to take A0 to be those rational functions which can, is there a question? No? It's good. I'm going to take A0 to be those rational functions which can be evaluated at 0, so that there's a well-defined notion of limit. There's no blowing up as Q goes to 0. And the theorem of Kashiwara and Lustig, the very beginning of their theory, is that any integrable UQG module V admits an A0 basis, so a basis that doesn't blow up at 0 of weight vectors, with A0 span that they call L, the crystal lattice, such that if we write B, so the BIs are going to be the image of these weight vectors VI. So remember, these weight vectors of VI apply for all values of Q simultaneously. It's a field of weight vectors, if you like. I'm going to take their image in L modulo QL. So that basically means I evaluate at Q equals 0, because quotienting out by QL is precisely quotienting out by those things which vanish at 0. So I evaluate at 0. The basis vectors I get at Q equals 0 are stable under these Kashiwara operators, these renormalized EI tildes and FI tildes as a set. So this is exactly the same phenomenon that we saw in the operator phase context before, but done in a more algebraic way using using ideals of using modules over the field of rational functions in the parameter Q instead of just over C and taking a limit as Q equals 0, as Q goes to 0. Okay, so that was algebraic quantum crystal basis theory done extremely quickly. A bit of terminology. The pair of the L and the B is called the crystal basis, although often people refer to just B as being the crystal basis because that somehow contains the combinatorial information. So that's the basis itself. And the set B, if I take account also of the action of the Fi tildes, which will give me the arrows in my diagrams that I had before, that's called the crystal graph of the representation V. And for any particular V, these are unique up to some reasonable notion of isomorphism. So now we can go back to our diagrams. This is the crystal graph in the sense of the previous slide for this 27-dimensional representation with highest weight 2 pi 1 plus 2 pi 2. And okay, that's for SL3, just to show that. Oh yeah, what I want to do, that's not what I wanted to do yet. So let's do something else. So as I said previously, the theorem about the existence of this crystal basis, so this set theoretic basis for my representations at Q equals 0, is really just the very beginning of the theory. What's amazing is that it simplifies not just the action of the generators EI and FI, but it simplifies basically everything in representation theory. So Clebsch-Gordon coefficients, branching rules, intertwining operators, all these kinds of things become basically 1-0 valued matrices, or perhaps, yeah, 1-0 valued matrices. And so are described in purely set theoretic terms using these crystal bases and crystal graphs. And the example I want to take here is the tensor product rule. So this is going to be crucial for what happens in the rest of the talk. I'm going to take a pair of representations, V and V prime, and I'm going to take their crystal bases, B and B prime. And the first fact is that that a crystal basis for V tensor V prime is given by B cross B prime, or if you like, B tensor B prime, the image of the tensor products of the bases B and B prime. That's a crystal basis for V tensor V prime, and that the action of the Kashiwara operators is given by this formula here, which is extremely simple because all it's saying is that either the Fi tilde, the Kashiwara operator, acts on the first leg and ignores the second, or it acts on the second leg and ignores the first. It's just one or the other. So again, this will be a 0-1 valued matrix, but just you have to choose which leg of the tensor product this is acting on. And the way you choose is with some, again, combinatorial condition. So you need to introduce these phi I and epsilon I maps. Phi and epsilon here are chosen to correspond to the letters F and E from before. So epsilon I is this quantity here, which tells you how many times you can apply the raising operator EI tilde before you kill your basis vector. And the phi I likewise tells you how many times you can apply the lowering operator Fi tilde before you kill your operator. So these are basically saying how far you are from the top and from the bottom in the particular SL2 sub-representation that you're looking at, corresponding to the simple root vector with index I. I'll show you some pictures of this in just a second. In fact, maybe straight away. Yeah, let's do a tensor product of SL2 representations just to see how this works. So here I've got the 4-dimensional and 6-dimensional irreducible representations of SL2 with their weight bases and the action of the F operator, the Kashiwara operator, in the crystal basis. So this is the set theoretic version. So the F is just acting as a lowering operator. It starts at the highest weight vector, and then it sends you successively to lower and lower weights. And under this Kashiwara-Lustig renormalization, this becomes just a set theoretic map on this basis, where this basis vector is sent to the next one, and so on and so forth. Okay, so the theorem from the previous slide tells us that the crystal basis for the tensor product is just the Cartesian product of these two finite sets. So that's our new crystal basis. And the only thing we want to know now is how the Kashiwara operators Fi tilde act on this new crystal basis. For that, I need to recall the law, which says that it acts on one or other of the two legs, depending on this these combinatorial conditions in terms of these functions phi and epsilon I. So I need to calculate phi and epsilon. So as I said, epsilon tells you how far you are from the top of the string. Phi tells you how far you are from the bottom of the string. And I compare these, and that tells me whether I act on the first leg or the second leg, and that gives this picture here, which gives straight away the decomposition of the tensor product V3 tensor V5 into 4 irreducible sub-representations of dimensions 3, 5, 7, and 9, respectively, so that I straight away get this decomposition V3 tensor V5 is isomorphic to V2 plus V4 plus V6 plus V8, which is the well-known rule for tensor products of SL2 representations. Okay, so that is just recovering something very easy by a fancy method. But what's great is that this works very easily in high rank as well. So just to prove that we can do other things, here's a couple of SL3 representations. V pi 1 here is the fundamental representation of SL3 on C3. V pi 2 is the dual representation on C3 star. Now we have 2 lowering operators, an F1 and an F2, and the way they act on V pi 1 here and V pi 2 respectively is by lowering, but you need to lower by F1. I guess the blue is F2, so you need to lower by F2 first and then F1 if you're here, and you need to lower by F1 first and then F2 if you're here. And if you take the tensor product and calculate using the tensor product rule of Kashiwara from a couple of slides ago, you find exactly this diagram, so that you see that C3 tensor C3 star, which is of course just endomorphism of C3, decomposes into an 8-dimensional representation like this, which is the adjoint representation, and a 1-dimensional representation like this, which is the trivial representation. So again, you get a nice decomposition rule for tensor products just by some extremely combinatorial set theoretic data, no calculations more complicated than, elementary school are required once you know the fancy setup into which this sits. Okay, and just a little remark while we're there. If you do the decomposition of the tensor product in the other direction, you get the same 2 components. So this adjoint representation and the trivial representation, but not situated in the same way. So it's not even just the flip map which intertwines these 2 decompositions. For instance, if I start at the highest weight vector here and go blue-red here, I end up in the corner. But if I start at the highest weight vector here and go blue-red, I end up in the middle. So there's a non-trivial intertwiner between V pi 1 tensor V pi 2 and V pi 2 tensor V pi 1. And this is extremely well-known phenomenon to people in quantum groups, that you have this braiding, that the tensor product of V tensor W and W tensor V are isomorphic, but not by just the flip map, by some braiding operator. And this is an instance of that showing up in quantum group, in crystal graphs. And just to, because I have scans of these things, here's another example for a couple of SL4 representations, just to show that these things are very calculable. Okay, all right, I have nothing to say about that. I just, I took the effort to draw these pretty diagrams and I wanted to take advantage of it. So sorry you have to watch me show off my primary school.
Robbie, out of curiosity,
yeah,
is that the same as the composition of tensor products of representations of the Wien group?
No, it's not. So we're talking about representations of the Lie.
Yes, but you have Weil-Schur duality.
Yeah, that's a good question.
And it's kind of seems like you're decomposing representations of a tensor products of finite group.
That sounds plausible, at least for the SL3. Oh, sorry, the SLN case.
Yeah, I don't know, just as asking.
Yeah,
feels like it somewhat.
Yeah, that's quite possible. Like you say, by duality.
Mm-hmm.
Well, yeah, but I don't know. Apart from the AN case, I don't know the theory well enough to say
okay
how that works.
Thanks.
Okay, I'll leave that as a homework problem. Okay, so that's crystal basis theory, including the tensor product rule. That was all Kashiwara and Lustig stuff. So that's 20, 30 years old now. So that, like I said at the start, the goal of this is not to redo that theory, but rather to crystallize the algebra of functions which is dual to the theory we've just been doing. And of course, we're going to use Kashawara-Lustig theory. That'll be a crucial component, but we're going to end up with a different kind of crystallization, which is much more operator algebraic in terms of graph C-star algebras and higher rank graph C-star algebras. So that's the next thing to do. Right. Okay. Quick reminder, quantized algebras of functions. I'll do this quickly. So for a classical compact group K, OK denotes the polynomial functions on K, which is the same thing as just the matrix coefficients of, I wrote irreducible integrable G modules. I guess that should just be integrable G modules, either that or I should take the linear span of the irreducible, the matrix coefficients of the irreducible modules. In any case, the polynomial functions are just these functions here, where I take a pair of vectors in a finite dimensional representation, and the function is given by taking k, sticking pi k into this slot, taking the inner product, and that gives me a function. Those are exactly the polynomial functions on my group. And if I take the norm closure, the C-star closure of this, after representing it, for instance, on L2 of k by multiplication, I get the continuous functions. That's just Stone-Weierstrass. Now I can quantize this super easily. I just put Q's everywhere and voila, we're done. Okay, so I just need to take irreducible, sorry, not irreducible, just integrable UQ, finite dimensional UQG modules, do exactly the same construction, and I'm going to define thus an algebra of polynomial functions on KQ and a C-star algebra of continuous functions on KQ, which now is a non-commutative algebra, unlike the classical case. And the non-commutativity comes precisely from this braiding fact that the tensor products of two representations are not isomorphic under the flip map, but under some more complicated map. And just a remark, more generally, we can define quantizations of homogeneous spaces K mod H, where H is any Poisson subgroup. So flag varieties, for instance, would be a nice example of this. Some historical remarks about this. So starting with Woronovich and Soyman and Waxman, and ending with Neshvev and Tuset, these C-star algebras were put into a continuous field of C-star algebras, so that in some operator algebraic sense now we can consider this as, you know, a family, a continuous family of algebras indexed by this parameter Q. Q strictly between 0 and infinity. And moreover, Giselson has proven that these guys are all isomorphic. As long as you're not in the classical case, obviously the classical case is commutative and the non-commutative case is, the Q different from one case is non-commutative, so those can't be isomorphic. But once you're away from the classical case, once Q is different from one, these guys are all isomorphic. At least the continuous functions are also isomorphic. The dense subalgebra of polynomial functions are not all isomorphic. They're somehow different dense subalgebras. Excuse me. But when you take their C-star closures by some, you know, flabbiness of C-star algebra theory, the norm closures are all the same.
But how do you actually prove it that they are not isomorphic? I mean, of course, we do not expect them to be isomorphic, but I remember one paper in which it was proven just for podless spheres. So it's not a very complicated algebra. And it was actually quite an argument to prove that when you choose different Qs, these polynomial algebras are non-isomorphic.
Yeah, maybe you're right, Piotr. Maybe I'm speaking too loosely there. Maybe this is not actually proven.
Because it's one of these no-go theorems, and it's not obvious which tools to use. I mean, this is algebra. You don't have all these operator algebraic tools. I mean, it's not exactly a big deal, but I remember that even for podless, it was non-trivial to prove that for different Q, these polynomial algebras are in fact, indeed, non-isomorphic.
Yeah, you might be right. I don't know whether, Marco, you have anything to say about that, but I think you're right, Piotr. I think I'm speaking optimistically there. Yeah. Everyone would believe that these are not isomorphic, but I don't actually.
I definitely believe it, but if you would ask me how to prove it, I would say, no, I wouldn't touch it.
I think for Q rational, they are different. So sorry, for Q roots of unity, right? That's
sorry. I should specify that I'm only allowed to consider in this talk Q being real. because
so for Q being real, that could be isomorphic.
I don't think so, though. And maybe
I don't know.
A good thing there, Richard, because you're right, for Q, a root of unity, these are definitely not.
So plus minus one, right?
For plus minus one, for instance.
Yeah,
but even just now using sort of meromorphic continuation arguments, I think we can say this would not be, oh, no, I'm not totally sure about that. I was going to say maybe these cannot possibly be all isomorphic, because then they'll be all isomorphic for every value of Q, including roots of unity, which is a contradiction. So, but I don't think that's a real proof. I think that's
no.
I
think Q plus minus one breaks things down.
Yeah. Again, in this talk, unfortunately, I'm not allowed to consider Q equals minus one.
Yeah. Okay. So I don't know. Right.
So,
okay.
Yeah. Okay. So let's just say these are not by the standard strategy of if you say something loudly enough, everyone will believe you. We'll see if that works or not. But certainly, everyone would. It's an extremely. We would be extremely surprised if these were equal for the in the algebraic case. Okay, homework problem. Second homework problem for the day. Where are we? Okay, so now we want to take a Q equals 0 limit of these algebras of functions, and this has been begun, this program. I mean, there are well-known and beautiful theorems about taking the Q equals 0 limit of this continuous field of C-star algebras, for instance. Starting with Voronowicz for SUQ2, and then Hong and Zemansky dealt with the quantum projective spaces, quantum spheres, quantum lens spaces as well, which I won't talk about. And Giselson has a work in progress on the case of SUQ3, all of whom have proven that this continuous field of C-star algebra, so the continuous functions on XQ in each of these cases, extends in some reasonable way. There's some reasonable limit algebras at Q equals 0 and infinity, in such a way that, as I said before, all the fibers for Q equals different to 1 are isomorphic, now including 0 and infinity, which was not allowed on the previous slide. And what's more, by studying the structure at Q equals 0 and infinity, these will all be graph C-star algebras. Now, just a warning that that's a lie, not graph C-star algebras. I will tell you exactly what they are in a second. At least for SUQ2, it will be an actual graph C-star algebra. And for the other cases, you need something a little bit different. What do you actually need? So, okay, first remark, again, homework problem, the OXQs are not all isomorphic. It's only when you take the C-star algebra closure. The Q equals 0 limit of the algebraic guy also has a name. It's called a Levitt path algebra, which is just an algebraic analog of a graph C-star algebra. You close up your Levitt path algebra with the C-star norm, you get the graph C-star algebra. But the more precise statement, which makes this theorem actually correct, is that for in the Hong-Zemansky case, it's not actually, it should actually be seen as the AF core of a graph C-star algebra. It's actually the circle bundle over CPQN, which is a graph C-star algebra. And then this is the gauge invariant subalgebra. And in Giselson's example, it's not a standard graph C-star algebra, but a higher rank C-star algebra, higher rank graph C-star algebra, so a 2 graph C-star algebra. Okay, not worry about the details there. And let me mention as well, as I mentioned at the start, there's another approach to the case of SUQN for crystallization, which is the approach described by Pal in his talk a couple of months ago, which is a rather different approach to all of this, but is another interesting way of renormalizing things correctly, so that when you take the Q equals 0 limit of these continuous fields, you get some nice C-star algebras.
And would it be reasonable to conjecture that when you look at SUQN, you will get it as at Q equals 0, you'll get it as n-1 rank graph C-star algebra?
That would be not just a reasonable conjecture, but a reasonable theorem.
Okay, even better. Okay.
Absolutely. So yeah, let's head towards that. So I need to tell you what a graph C-star algebra is, graph algebra. So we start with a directed graph. So lambda 0 are the vertices, lambda 1 the edges, and I'm going to write lambda for the paths in this graph. And the paths form a category, because you can concatenate 2 paths. They have a source and a target. Any path has a source and a target, and as long as the target of a first path is equal to the source of a second path, I can concatenate them, and that makes paths into a category. And if you look at the length function, this is a function on this category, which is actually a functor. N is a monoid, and a monoid is a type of category as well. And this length function is a functor from the category of paths to the monoid of positive integers. And then we'll define the Levitt path algebra, which, as I said before, is the algebraic version of a graph C-star algebra. And it's called KP star lambda here. KP refers to Kumjian and Pask. We're going to get to them shortly. You could call it other things, but let me go with that. Is the... oh, hang on a sec. Un peu plus tard, ça pourrait... Oui, évidemment. Ça marche. Merci. Yeah, so how do we define these Levitt path algebras? Well, they're star algebras generated by a bunch of projections indexed by the vertices and a bunch of partial isometries indexed by the edges, satisfying some basic conditions. The first thing is that the vertex projections are a family of mutually orthogonal projections. The next thing is that if I take the partial isometries and I do SE star SE prime, that this will be zero unless the edges coincide. And when the edges coincide, that product will just be the source projection. So the projection of the vertex of the source of E. And in the other direction, if I do instead SE star, I won't get the range projection. But if I sum over all edges that have target the vertex V, then I get the range projection. So there's an inequity between the source and the range projections in this definition, which is what makes graph algebras interesting. These partial isometries have different behaviors at the source and at the range.
Sorry, don't you assume in 3 that V is regular?
Yes, I mean, this is an incomplete definition.
Yeah, so, okay, yeah, you're right. This is an incomplete definition. I should add probably some extra conditions as well. I want everything to be finite. I don't want any infinite graph. And then my life becomes a lot simpler. So, yeah, thanks for the clarification, but I propose that from now on, everything be finite. Everything be without sources or sinks, and everything be, et cetera, et cetera. Everything is.
No, you're just good with being row finite, then it's all right.
Exactly, yeah. But just to avoid me saying stupid things in the future, I propose that now and forever we make our graphs as nice and pleasant for the graph system as possible, so that all. So that my definitions become simpler.
But let me object to it, because in fact, as much as it seems reasonable to say, okay, let it be row finite, why not? These are nice regular graphs. I mean, you go to these CPNs of Kong-Szymański and it's no longer row finite. So
yeah, that's well, I mean, they'll be finite as long as I'm allowed to see them as the AF core of a finite.
Exactly, yeah. So that's
right within the passage the AF core, then yeah. Become worse. But I want to avoid that. So I'll, rather than talking about those kind of graph C-star algebras, I'll just talk about AF cores of finite graph C-star algebras.
Yep.
And again, my life becomes much simpler and I'm much less likely to say stupid things, which, is a win for everybody. Okay, so those are the graph C-star algebras, but now, but before we go on, let's just do the basic examples, because, it's mandatory when you introduce graph C-star algebras to give these basic examples. So C-star algebra generated by a single unitary is given by this graph C-star algebra here. And of course, that's just continuous functions on the circle. If now my unitary becomes a partial isometry, which is described by this graph here. So this second partial isometry will be the inclusion of the complementary part of the range of this partial isometry. Then I get, so this C-star algebra would just be the C-star algebra generated by a single partial isometry, which, as we know, is the Toeplitz algebra.
Sorry, could you go back to the previous slide just for a second?
Yeah, sure.
You do it of a range. Okay, so I have this inverse convention. Okay.
That's one of the many painful things And I'll probably say things the wrong way around at some point, but yeah, okay. You people are nice, so you'll forgive me for such.
But yeah, consistent. This is what I checked. We are consistent. So.
Okay, so now if we add to this Toeplitz algebra graph, we add one more loop on the other side. What we get is the algebra of continuous functions on SUQ2. So this is a three-sphere, if you like, and this is due to Voronovich. Okay, and then the Hong-Szymanski result. As I was discussing with Piotr just a second ago, rather than dealing with the functions on CPN, I'll deal with the functions on the circle bundle, canonical circle bundle over CPN, and then I get a finite graph algebra generalizing the first one like this. You know, SUQ2 being a circle bundle over CP1, for instance, gives exactly one of the instances of this. But yeah, so this is the Hong-Szymanski result written in terms of graph algebras.
Mm-hmm.
So the big question is where do these graphs come from? How do Hong and Szymanski, why should we believe Hong and Szymanski when they tell us that this is the right graph? And can we do higher rank examples? So these are all in some sense rank 1. I mean, this as a homogeneous space, this has a rank 1 behavior because it's a quotient of a.
Robert, just please allow me to jump in for a second. I mean,
Sure.
you used a word which triggered some memories, namely, why should we believe Hong-Szymanski? Now, I hope Francesco is in the audience. Yeah, I think Francesco is in the audience because at a certain moment, yeah, it's Tomek, of course, because at a certain moment, for whatever reason, we just wanted really to verify this result of Hong-Szymanski and indeed prove that when you take the good old-fashioned Waxman-Seuberman quantum sphere sister algebra, indeed is isomorphic to the graph sister algebra of such a graph. And it turns out that it really takes quite an effort to clarify the proof. And the result is definitely correct. That's what we concluded. But it needs a far more sophisticated argument. Yes,
Piotr, sorry. Maybe we should say that for the sister algebra closure inside the universal FCQN, it was done in the paper by Mikkelsen and Cad, right?
Yes,
and
yes.
then they explained to us that you can adapt the same proof to the universal sister algebra, and it is quite an effort. Yes, and you prove that these two are the same, but yeah, it's not easy.
So that's really, yeah, thank you, Francesco. That's really, and of course, we immediately got in touch with Wojtek, and he admitted that the argument that he used in his paper, in his original paper, needed more clarification. So he couldn't defend his argument as it was published, but thanks God, one way or another, you can just go around it and somehow it works at the end of the day, but it's just a bit more subtle. Yeah.
Well, in any case, by the end of this talk, we'll have a second possible justification for why this is the right graph C-star algebra for this particular quantum space. So, we're now absolutely sure that Hong and Szymanski are trustworthy, which, of course, we knew from the start, but it's good to have confirmation that everything's shipshape.
Yeah. There's actually a silly mistake in the arguments, and the argument as such was wrong, but you could correct it by going into a different quotient algebra and then we could. Right, okay. Francesco, do I remember it correctly?
Yes, yeah.
Okay, thank you.
So what we need now is the notion of a higher rank graph, if we're going to do higher rank examples, so a K-graph. So what's a K-graph? So a K-graph is, again, a category of paths with a morphism measuring the length. We'll now call it a colored length because it's not given by a single integer, but by a K-tuple of integers, where each of the elements of the K-tuple corresponds to a different color, let's say. And satisfying this factorization property that if I have a path E of colored length m plus n, certain n tuples, k tuples m and n, then there's a unique way of decomposing that path as a concatenation of two smaller paths with colored lengths respectively M and N. Okay, so the standard way of illustrating such a high rank graph is with a graph with colored edges like this. This is not, strictly speaking, fully enough information to completely describe the K-graph, the 2 graph in this case, because of the 2 colors. But let's use this nonetheless as an idea. So what we're doing here in this graph is we're using the dots to represent the vertices. So the vertices are just the paths of colored length 0, and we're using these colored edges to represent the singleton edges, that is the edges of color with just a single 1. So one color, length 1 in a single color and length 0 in every other color. This is sometimes called the 1 skeleton of the high rank graph. And the point is that there's some equivalences in this. So if I go red, blue, blue, for instance, that path should be the same, considered the same in my K-graph as the path blue, blue, red, or as the path blue, red, blue in this diagram. All of these are considered the same path because they need to, the decomposition needs to be unique. And they're just different ways of decomposing the same path as a path in reds and blues. So somehow you're allowed to go diagonally across certain squares where the colors are allowed to change order. Okay, so this is what a K-graph is. I won't give any more detail than that.
So if I understood it correctly, could you go back? Yeah. So here the point is that, for instance, if I want to go from left bottom to top right, whichever way I go, I will have to use 2 blue and 1 red.
That's exactly right. Whichever path from here to here I use will be 2 blue and 1 red. And on this 1 skeleton picture, I can represent that in different ways. But perhaps the most natural way is to see the path from here to here as being the 2 squares.
Exactly. Yeah.
So the 2 squares is really what the 2 path is from
exactly.
this to this corner. And then if I want to decompose that 2 path as, say, a red path and a blue, blue path, then I can do it by this, red and then blue, blue. Or if I want to decompose it as a red path, sorry, a blue path and then a red, blue path, then I can decompose it in this way. But it's still the same path.
Yeah.
Great. And then using this, we define the Kumjian-Pask algebras in the same way as we defined the Levitt path algebras before. So Kumjian and Pask, of course, didn't define the Kumjian-Pask algebras. They defined the higher rank C-star algebras, which are the enveloping C-star algebras of these guys. Kumjian-Pask algebras were the algebraic version, which were introduced afterwards by Antwerp and Rayburn and other people. Yeah, so how do you do it? Well, you just have a bunch of projections indexed by vertices and partial isometries indexed by paths, such that, again, the vertex projections are a mutually orthogonal family, that the SE star, SE primes, where E and E prime are of same colored length, will be non-zero only if the 2 paths E and E prime are identical. In that case, you get the source projection. And likewise, if you take the sum over all range projections for all paths of a given covered length that arrive at a given vertex V, then that will give you the range projection, the vertex projection PV of the target vertex. Okay, so this is, again, just some abstract algebra, star algebra that we can define. And then you can
wait, just a second. So when DE is not equal to DE prime, you say that this product is 0, right?
No, that's not totally correct. No, when D is not equal to D prime, what I could do, for instance, if E prime is strictly longer than E in length, then I could decompose it by the uniqueness. I could decompose it as a path of length E and another path. And so it becomes, it's not explicit in these relations.
Yes. Thank you. Yes.
But you can deduce from these relations, if they're of unequal length, you can use some decompositions to deduce.
Of course, you're right. But now let me have a serious question for a change.
Sure.
You see, it's a nice result for Levitt path algebras. That, well, you take the graph sister algebras as the universal enveloping sister algebras, but Levitt path algebras are always sub-algebras inside. So typically when you take the universal enveloping sister algebra of a star algebra, it's not in general true that the star algebra is a sub-algebra. You might have some quotient before completion when you do this universal construction. And for Levi-Pav algebras and graph sister algebras, we can prove that taking this universal construction actually doesn't require doing any quotients. Okay, you really have it always strictly as a subalgebra. So now my question is, do you have the same result for Kumji and Pass? Is it always a subalgebra in its completion in the higher rank graph sister algebra, or not necessarily so?
So unless I'm mistaken, yes, at least, I mean, I'm no expert in higher rank graph sister algebras, unfortunately. I've been learning this on the fly. Let me stay in the finite case so that I'm not likely to make any stupid mistakes. There is a faithful representation of these Kumji-Pass algebras, and that's enough to get the injectivity of the...
But then I believe it's true, yes, okay. Okay, good.
Okay, so so we have these higher rank generalizations. And the main theorem of the talk here is that if K is a connected compact semi-simple Lie group, and we consider this continuous field of C-star algebras, the continuous functions on the quantized groups KQ, then these can be extended to Q equals 0 and infinity in some natural way, which I'll have to describe later on in this talk, such that at the limits 0 and infinity, we get precisely a higher rank graph C-star algebra for some higher rank graph lambda. Firstly, of rank, the rank of this higher rank graph is exactly the rank of the compact group, that is the dimension of the maximal torus. Moreover, we can make explicit what the higher rank graph is. We can write down exactly what this higher rank graph is. So it's not just an abstract result, but actually a concrete result of isomorphism with a particular higher rank graph C-star algebra. As I said before, this is known by Giselson for SUQ3, and of course by Ronovich for SUQ2 as well. And Giselson actually proves much more. He shows not only that these are graph C-star algebras at the limits of 0 and infinity, but in fact that they're all isomorphic for every Q different from 1. Again, under the C-star completion, we wouldn't expect this for the Task subalgebras, but for the C-star completions, Giselson shows that this is true for SUQ3. And it's a very natural conjecture now to suppose that this would be true in generality. That has not been proven, but I expect that if someone was diligent and followed through Giselson's arguments, you can prove this isomorphism in absolute generality. And the other remark is that you can replace the group K by the canonical torus bundle over a flag manifold in the same way that we were doing with Hong and Zhemansky, and then you'll recover Hong and Zhemansky's isomorphism result from the slide before with exactly the graph that we were discussing previously.
Wait, so you are saying in particular that when you look at this isomorphism in your remark number 1, this isomorphism is U1 equivariant, right?
It is U1 equivariant.
Okay.
So it's a gauge equivariant action, and that's why when we pass to the AF core in the second remark, we get indeed the algebra of functions on the base space.
But actually, wait a second, you can also perhaps say more, isn't it? Because if lambda is a 2 graph, right?
Yeah, sorry, yeah, you're right.
But the action is by T2, right? So, okay.
It's a TK equivariant isomorphism.
Okay, perfect. Thank you.
Here's some pictures. So this is Giselson's picture. This is the case of SU03. And for people that know a bit about representation theory, this obviously looks just like, very like the Bruhat graph. But, you know, as Giselson points out, it's not exactly the Bruhat graph. There's actually a couple of extra arrows here. This long diagonal arrow and this other long diagonal arrow, which are not represented symmetrically. When Marco and I first saw this result of Giselson, I won't speak for Marco. I had stupidly imagined that Giselson had maybe made a mistake and that, you know, maybe he'd just forgotten to put the other 2 arrows in the diagram. But he's absolutely correct. This is a non-symmetric diagram. It's exactly this 2-graph algebra which gives SU03. And when we go to show that we can do another example, well, this is a calculation that Marco carried out for SPQ2, which again is a rank 2 group, so now type C2, and you get this graph two graph here, obviously much more complicated. And importantly, it's more than just the, here the elements are in correspondence with the Weil group. Here it's the outer elements which correspond to elements of the Weil group. And there's two additional elements inside which don't have loops on them. So they're somewhat different from the others. But okay, we start to see that the graph we don't have a good conjecture that would immediately tell you what this graph is. We have a procedure, which I'll describe hopefully now. 10 minutes, an hour and a half is shorter than I thought, Pierre. I'll try and describe very quickly the procedure for producing these graphs. It's very explicit, but it takes some calculation. You don't have a conjecture for just writing it down in terms of the structure of the Weil group or the Bruhat graph or something like that. Okay, so that's the question, how to compute these K-graphs. And that's what we need to do. And so I'll go as far as I can in 10 minutes and then we'll call it a night. So what are we going to do? So a little bit of background to start with. So let's take V lambda, an irreducible representation of highest weight lambda, and let B lambda be its crystal graph. So this finite set with basis elements. If I've got a tensor product of crystals, I'm going to call the Cartan component the irreducible component in the tensor product decomposition, which has the highest weight, lambda plus mu. There will be other components with lower highest weights, and this is the highest weight possible. And moreover, we'll say that two elements in B lambda and C in B mu are composable if their tensor product lands in this Cartan component, this component of highest weight. Okay, so in this picture, for instance, all the elements in this part here are in the Cartan component, and these guys are not in the Cartan component. So that, for instance, B4 tensor A4 is composable, whereas A4 tensor B4, which is on the other side, is not composable because that lands in this four-dimensional guy here. So composability, again, is a non-commutative relation. Okay, so that's the Cartan component. And then we're going to talk about right ends of a simple module. So we take an irreducible representation B lambda, and I'm going to take another positive weight, which is strictly less than this highest weight lambda. And because it's strictly less, I can inject B lambda into the tensor product of B lambda minus nu, tensor B nu, as the Cartan component. It is the component of highest weight in the decomposition of this tensor product. So I have an inclusion of this inside here, and that allows me to define the right end. So the new right end of a crystal basis element for B lambda is just where I decompose it according to this tensor product here, and I just take the second leg. So I'm realizing my crystal basis element in B lambda as an element in this tensor product, and I'm just taking the right-hand end of that tensor product. Okay, that's a thing I can do. And in particular, first we have a little lemma that tells you about composability. So it turns out that B and C, two crystal elements, are composable if and only if the fundamental right ends. So I'm now not going to separate off a large highest weight nu, but just a fundamental, the smallest possible highest weight pi I here. And if I separate off this pi I component for every I, and those guys are composable with C, then B itself is composable with C. In other words, to know the composability of B with C, I just need to know the right ends of B, the fundamental right ends. So I don't need to know all about B, I just need to know how its right end looks under any one of these tensor products where I just snap off a fundamental representation on the right-hand side. And now we can define the higher rank graph. So we'll put R to be the rank of the group so that the dominant weights P plus are just this monoid of n tuple, R tuples of positive integers, where I associate to an n tuple of an R tuple of positive integers, just the linear combination of the fundamental weights here. And then I'm going to define a high rank graph by taking just all possible families of fundamental right ends of a crystal basis element of, in fact, any crystal basis for any irreducible representation. I've taken B rho because that's the smallest possible one in which I can have all of the fundamental representations. Oh, that should be pi 1 up to pi r, by the way. Sorry, there's a typo there. That should be an r. But B rho is the smallest one that contains all the fundamental representations as a right end. But I could, in fact, take any larger representation here and I'd get exactly the same set of vertices. And then an edge will be a vertex followed by a crystal basis element of any irreducible crystal, with the only condition that B needs to be composable with all the right ends appearing in this vertex. So I've got a bunch of fundamental crystal elements and a longer crystal element, and I just need to be able to compose that longer crystal element with each of the fundamental guys in such a way that I always land in the Cartan component. That's what the edges are, rather the K paths, the lambda paths. Okay, and the theorem is that, that we have this isomorphism between the Q equals 0 limit of the Levitt path algebras and the Kumjian-Pask algebras of these higher rank graphs. And likewise, if we take the C-star completions, we get exactly the same thing. So this recovers Voronovich's results and Hong and Zemansky's result if we generalize this slightly to homogeneous spaces, which we're allowed to do. Did I make that as a remark? No, I didn't make that as a remark. We can also generalize this to homogeneous spaces and you get a similar kind of calculation for the graph, and it gives you Hong and Zemansky's result back. It also gives you Giselson's result, but in fact, it lets you generalize this to now whichever quantized semi-simple Lie and compact semi-simple Lie group you care about, or any flag variety to torus bundle over a flag variety if you don't want to have to take the AF call. Okay. That gets us to everything I absolutely wanted to say. So, because it gives us the fact that these Q equals 0 limits are very simple star algebras, or C-star algebras, if you like. Why do I say very simple? Because they're generated by projections and partial isometries, which means 0, 1 valued matrices, but now in an infinite dimensional setting. So partial isometries here could be infinite dimensional partial isometries, but it's in the same spirit as Kashiwara and Lustig, that our algebra of functions at Q equals 0 is again given by 0, 1 valued matrices, generated by 0, 1 valued matrices. It's just that it's now infinite dimensional theory instead of finite dimensional theory. Okay, and if I had more time, I could say a bit about the proof.
Yes, let me ask a simple question, please.
Yeah, for sure.
Of course, there is isomorphism at the level of Kumjian-Pask algebras implies the C-star isomorphism, right? I mean, if these two star algebras are isomorphic, then so are the universal enveloping C-star algebras. Okay, if you would look at this stronger algebraic statement, because it applies with C-star algebraic, so it's stronger, would you be able to fiddle with a field? I mean, change your field of coefficients? Do you really need to rely on complex numbers? Or maybe you could even venture into having them over some nice commutative ring? I mean, does this isomorphism at the level of Kumjian-Pask, does it really use some special properties of complex numbers, or you can just go beyond it and formulas do not depend on it? Because many things in Levitt path algebras can be done over commutative rings.
Yeah, I'm hesitating because the way our proof works, and this is something I won't say, but I'll show you the slide, is this theorem here, which is a key theorem along the line of the proof. If you take an element of these polynomial algebras,
yes,
at any Q, where we're taking Q being over the ring of rational functions which can be evaluated at 0. So algebraically, it makes sense to talk about the limit of this as Q equals 0. Then the Soibelman representations corresponding to the symplectic leaves of the Poisson structure on these compact Lie groups, those Soibelman representations as Q goes to 0 also admit norm limits. They don't blow up either. So there's some coherence between the algebraic notion of the limit at 0 and the Soibelman C-star algebraic analytic notion of convergence at C equals 0. That's the only point at which I'm not confident enough to say that you could do something in a more general situation. You know, in the spirit of pure optimism, I'd love to say, yeah, I think you're absolutely right, Piotr, but I couldn't back that up at the moment with any mathematical argument. It's just,
okay. Yeah.
I think it's a perfectly reasonable conjecture. I think, I think that's is a good idea, but I don't know how to prove it. Okay. So then you've allowed me to, even in the dying minutes of the talk, to even mention a key moment in this proof. It's based on work of Stockman as well, importantly, based on important work of Stockman, where he gives generators and relations for these algebras of polynomial functions. That's really the key starting point, and then you need to apply this, do a little bit of fine analysis of these Soibelman representations to see that these Q equals 0 limits exist. Once you got that, the choice of, there's a fairly natural, I won't do all this, but there's a fairly natural choice of generators in terms of these matrix coefficients, which gives you the Cumgen-Pask relations, and the rest is accounting and an application of the gauge invariant isomorphism theorem, which is a now famous, well-known result about the structure of higher rank graph C-star algebras. And probably with that little technical remark, that's a good place to stop and hand back to you, Piotr.
So I understand this is a right end for your talk.
That is right.
Okay, so thank you very much. Okay, let's continue with questions. Any further questions? Tomek, Richard, Francesco raised his hand. Okay, Francesco, I saw you first.
Yes, so actually I have several, but maybe very short questions. So if I understand, it is not yet proved that the C-star algebra is independent of Q, right? You only studied Q. Okay.
Yeah, but after SU, so like I said, Giselson did it for SUQ3, and then there are the previous results due to Hong, Szymanski, and Woronovich for the rank 1, for the CPQs, and for SUQ2. But apart from those low rank examples, yeah, we don't know.
Okay, so there is no general strategy. I mean, or you have already an idea?
Oh, yeah, I think there's a strategy, and the strategy is given by Giselson. Giselson's a great expert at this stuff, and he's told us how to prove. So we know that. Oh, sorry. Oh, I can't remember. I'm sorry. I've got a hole in my memory. Giselson has proved that they're all isomorphic for Q different. No. Excuse me. Hang on a sec. No, he's proven results about the K-theoretic structure. So yeah, no, we don't know yet. But Giselson's strategy should be the right one to work. And the strategy works by a sort of Jordan decomposition. So these algebras have a decomposition series which corresponds to the decomposition of the symplectic, of the manifold K according to its symplectic leaves of decreasing dimensions, so a sort of cell decomposition, except it's not a CW complex, but still you have symplectic leaves of different dimensions, and you start off at just the 0-dimensional ones and prove that it's isomorphic there, and then you go, successively dimension after dimension, you prove an inductive argument. This is Giselson's strategy, and I think there's every hope that would work, but yeah, we have not embarked upon that, and I don't know how easy or hard it would be yet. I haven't looked at it in enough detail.
Okay, thanks. So now the other question is, I don't understand if it is proved that these are not graph C-star algebras, that you really need a higher graph for SUQ3, for example. Is it known that is not isomorphic to a graph C-star algebra?
Yeah, that I don't know. So there's some recent results. I should have mentioned that as well by Karen Strong and Ray Aubourgeois, and I forget who the other people are, but they have some abstract results which state that a lot of these C-star algebras are graph C-star algebras, but without making explicit what the graph C-star algebras are. It's done via ingenious methods using classification theory.
Yeah,
so
that you mean for flag manifolds, right?
Yeah, exactly.
So that was actually my other question. No, my point is SUQ3. Do we know that is not a graph sister algebra that you need a rank 2 graph? Can you prove that is not?
Yeah, I mean, it is a fact about the primitive spectrum. It's a comment in the end of the introduction read in Hong and Szymanski that somehow for graph algebras, you can only have a torus, a circle, I mean. So
yes.
U1.
Yes.
Okay.
And
Yes.
you always get some higher dimensional tori. So this strategy simply, I mean, these algebras really cannot describe that.
So you mean you can only have a circle? Or,
yes. Yes.
Okay. And for about the flag manifolds, which kind of flag manifolds can you get from this construction? You mentioned. So you mentioned that you can recover on Szymanski result, but so can you deduce the graph of any flag manifold? Or?
Yeah, and it's basically the same thing. The only thing that differs is what you use for your monoid. So where were we? So here, the monoid that I used was the whole monoid of positive dominant weight, dominant weights. If you go to a flag variety, let's start with the canonical torus bundle over the flag variety. Then you just use some sub-monoid, sub-lattice of this the full highest weight, the full set of highest weights, which corresponds to the parabolic.
Because I mean, what I don't understand. So it's not that you get this from the higher graph of the group. It's just, I mean, independently you derive the graph of the flag manifolds. Because as SQ3, I see a graph with higher graph with finitely many edges. While CP2Q, for example, we know that has infinitely many edges.
Yeah, the vertices may be different. The vertices of the graph may be different.
Okay. Okay, but in principle, so the result of Strung, Boachal, and so on, you can derive it from this construction.
Yeah, that's true.
Okay. Okay, thank you.
It would help if you would unmute yourself. I mean, we cannot exactly read your lips.
I forgot to unmute myself. Sorry. My question is about the duality. If you have this Q difference from 0, then you have this, on the purely algebraic level, you have this duality between this quantized logarithmic algebra and this coordinate algebra. Does it degenerate at Q tending to 0, or what is going on?
Yeah, so, I mean, what does this Pontryagin duality mean? You need, to make sense of that, you need the whole Hopf algebra structure, or at least a bialgebra structure. And we haven't, I guess, yeah, let me just think carefully before I say something stupid. So let me start by stating this. At Q equals 0, there is no longer a Hopf algebra structure.
Yeah.
So talking about Poincare duality, you know, we're no longer in the world of official quantum groups, so it's a little dangerous. There is nonetheless a certain notion of duality, and I think this is best encapsulated by the kind of Poisson or quantum duality that I was referring to right at the very start of this talk, the realization of these algebras not as the algebra of functions on KQ, but as the algebra, the group algebra or group C-star algebra of KQ hat. And as I mentioned before, so KQ hat being the Pontryagin dual when Q is different from 0. And as I mentioned right at the start, the quantum duality principle says that KQ hat as a quantum group should be seen as a quantization of AN, the AN group in the Iwasawa decomposition of the complexification of K. And this is not just, I mean, this is to begin with a philosophy, but it's also backed up by various concrete theorems by various people that I could list, but I won't do that right now. We could go into more detail if you want. But what that means is that when we get to Q equals 0, what we have is something like a crystallization of the upper triangular group. You know, if we take the SLN example, we have something like a crystallization of the upper triangular group, the group of upper triangular matrices with positive diagonal coefficients and trace zero, something like that, which is now a non-compact Lie group, and so has infinite dimensional representations, unlike K. So that while Kashiwara and Listic's crystallization stays purely in the finite dimensional world of finite dimensional modules, when you crystallize these function algebras, you're now in the world, you're philosophically, you're crystallizing the AN group, which is non-compact, and so you're going to get a family of representations which are now infinite dimensional. And the infinite dimensional representations will still be given by partial isometries, just like in the Kashiwara-Lustig theory, but they will now be infinite dimensional partial isometries. As people from graph C-star algebras know, the representations of graph C-star algebras, irreducible representations of graph C-star algebras, are typically infinite dimensional and not finite dimensional. So that's what's happening, where, you know, I'm not giving you a very concrete answer here, but philosophically what's going on is that we're crystallizing the Poisson dual group of K and seeing its representation theory as Q goes to 0. I don't know if that's a satisfying answer or not. It's the best I've got.
I'm satisfied. Thank you very much.
Excellent. Is anybody else?
May I?
Yeah, go ahead, Richard.
Yeah, just continue this question. So in principle, what you're talking is the formation of representation theory of AN group, right?
Yeah.
And you're asking what happens when Q goes to 0. So AN is a very nice group. So it's a very easy, of course, because it in terms of representations, but it's not that complicated. The structure is kind of very algebraic.
Yep, it's a nice.
Right, so we should be able kind of to see. So in principle, you are trying to say that if you even deform the group for Q non-zero, you would get essentially the same group, right? That would be
according to the Giselson principle,
this your C of O of KQ should be more or less constant as Q goes to 0. And when something happens as Q equals to 0. And I think there were lots of people working hard on what happens with this representation theory of nilpotent or solvable groups when you deform them.
Yeah, I mean, I agree.
I'm just curious.
Yeah, I agree with this philosophy, but this should somehow be related to, you know, something like Kirillov theory or something where you look at
yeah, but this representation theory, that's fairly straightforward.
And you look what happens, you know, as you quantize the symplectic, you know, the coadjoint orbits.
Yeah, but that's for nilpotent representations, you pick up a character and on A, and then use this to consider representation of nilpotent group. These are essentially very straightforward. It's Kirillov theory, yes, but it's not. It's kind of not difficult. It's algebraic. Distinction to general solvable groups. That's algebraic. So there should be control over what happens as Q goes to 0. Actually, should be more or less independent of Q.
Yeah, I think this is a good philosophy, and it would be interesting to try and make that statement precise.
Yeah. Okay. So well, just a question. I have no idea. Just a feeling.
No, it's great philosophy.
Thanks.
Yeah.
It's nice lecture. Thank you for your lecture, by the way. Very nice lecture.
Yeah. Any further questions or comments or queries?
I have.
Hello, Ludwig. Go ahead.
I have a question to Robert, to everybody, to Richard, to Piotr, to Marco, to everybody. just would like to dwell a little bit on this non-isomorphism, algebraic non-isomorphism. Does it mean, is it not following from the fact this non-isomorphism for this algebras doesn't follow from the fact that the Podlev spheres are not isomorphic? Or maybe you cannot find isomorphism which lives invariant some particular subalgebra, cell algebra. At least this.
That sounds pretty plausible to me. I think you should be able to, once the Podlev spheres are not isomorphic algebraically, then all these other groups should contain Podlev spheres.
Exactly, yes. Yes. Of course, you are right if you can show that you always have Podlev sphere inside. But do you? I'm not sure.
Yes, you do. Yes, you do.
Of course, yes. Yeah, but that is very well known. I mean, no, sorry, I take it back. No, it's actually, no, it's yeah, it follows for SEQ too. I agree.
Perhaps only add that I was talking about this with Kenny de Kommer, and he just told me that in principle, the argument, I think it's in a paper by Uli Kramer, could be directly adapted to just show the general case as well.
Okay, because that's exactly the paper by Uli Kramer who settled it.
It's not written down anywhere, so in principle it's open. But those that have looked into that paper say how it can just be adapted. Yeah.
Okay. Yeah, I'm very happy with this. These two comments. Yes. Yeah.
Thanks.
Yeah,
all right, so maybe it's time to wind it up. I don't see any further volunteers who would like to be satisfied with Robert's. Adam, how about you?
No, I don't have any questions. I just thought that it was about to finish, and then I showed myself to clap.
Yeah, that's a good idea. So let's thank our speaker again. Thank you so much. This was a very interesting talk. We really enjoyed it. And this way, our academic year 22-23 has come to an end. And let me stop the recording.
Well,